Hi. So we know something about the nucleus. Okay, it's some nuclei are small, some are big. Now, the smaller nuclei are very stable, and the larger ones are really unstable. Why? Let us see. So, if we take a nucleus, okay, this one, a large nucleus, and this one is smaller. Now, which one will be more unstable? Clearly, this one, because you have some protons in this one, okay, and some neutrons. You also have protons and neutrons in this one, but what's the difference? The thing is, within the atom, two forces come into play. You already know this: the electrostatic force between the protons, the force of repulsion, and the strong nuclear force. Okay. Now, if we talk about the smaller nuclei, the electrostatic force, of course, is larger between two protons, but at the same time, the nuclear force between these two is also very large. And in effect, the nuclear force dominates, and the small nuclei are very stable. Now, in terms of larger nuclei, they are not, because the nuclear force drops sharply. Okay, so nuclear forces, when two very closely, the protons are very close, then you have an appreciable strong nuclear force. But when they are far away, like at the two ends of this nuclei, the nuclear force drops sharply. And in some numericals in physics, we consider nuclear force to be not acting at a distance of 2 femtometer. Okay, so that's how sharply strong nuclear force drops, but it is the strongest of the fundamental forces. Now, in this case, the Coulomb force dominates between these two, between the ends. The Coulomb force will dominate, and this nuclei will break. Okay, so that's why heavier nuclei are more unstable. Now, the breaking down of these heavier nuclei is known as radioactive decay, and for nuclei with atomic number is greater than 210, so all of them undergo something known as alpha decay. What is it? We'll study. So say we have an element X, okay, it has Z number of protons and A is the mass, atomic mass number. Now what happens in alpha decay is the nuclei or the atom itself converts to another element, let us call this Y, the diff, and okay, so we will solve this later, with release of helium nuclei. So what is this is what helium nuclei looks like: 2 protons and 2 neutrons of 4 at the top. Now, of course, if the two protons are getting subtracted from Z, so we have Z minus 2 there, and 4 nucleons are getting subtracted from A, so we have A minus 4 over there. This is what happens in alpha decay. So let me give you a quick example. So bismuth, okay, 83, and it has a mass of 212. Okay, it undergoes alpha decay, so we can write alpha decay over there just to show you what's happening. A minus 4, so it's 208. Okay, 208, Z minus 2, 81. This element is known as thallium. Okay, so bismuth undergoes alpha decay, forms thallium element, so we're forming a new element over there, and we have a release of helium nuclei. This is a good example of alpha decay. How does alpha decay happen? So you have a atomic large nucleus, it will decay itself into a smaller nucleus. This is it, and this one, since it's smaller, it is stabler and more stable than this one. Now, how does energy go about in these equations? So if you have some energy in this case and some energy in the right hand side, how do these relate? It turns out the rest mass energy of bismuth is greater than the rest mass energies of thallium and helium, and this is true for every alpha decay. Okay, now what is the energy of this rest mass? Okay, it's m mass of this atom, so mass of x z a times c square. E is equal to mc square, where m is the rest mass, and what's the rest mass energy of y? It's pretty obvious, isn't it? Z minus 2 a minus 4 c square plus the mass of helium nuclei times c square. E is equal to mc square. That's the direct application of E is equal to mc square. If you calculate, this energy will be greater than these two, so we have some excess of energy. Where does this energy go? It goes into the kinetic energy of these alpha particles, which alpha into the kinetic energy of alpha particles which get emitted during alpha decay. Helium nucleus in one sense. Now if I label this as ui, initial energy, and this as uf, final energy, and take the difference between these two, so you have an energy difference ui minus uf. What is the energy difference? That's easy. That's the initial energy ui, okay, minus what's the final energy? Final energy is the sum of these two. Mass of this element y, z minus 2 a minus 4 plus the mass of helium into c square. And you can factor the c square and open these brackets. You get ui minus uf equal to mass of our initial atom, our parent nucleus, minus the mass of our daughter nucleus and the mass of the alpha particle. Okay, so you can factor the c square. This is what we get. Let me box this equation so you can see this clearly. So this value ui minus uf, so initial energy minus the final energy, is called the Q value of a reaction. So we can write this as Q equal to mass of parent nucleus minus the mass of daughter nucleus minus the mass of our alpha particles. This is a complete equation, and the Q value tells us if the reaction is feasible or not, because if the Q value is negative, then the mass won't decay itself. So that was not for today. We studied alpha decay, which happens for all a greater than 210 exhibit this. That's the general equation. XZA gives YZ minus 2A minus 4 and a helium nucleus, an example. And then we study what's the Q value. So Q is initial energy minus the final energy. So this is the important thing, is the Q value is not only defined for alpha decay. You have many other processes as well. You have beta plus decay, you have beta minus decay, you have electron capture. So the Q value, this is the general formula for Q value, ui minus uf. So if anyone asks you the Q value of a reaction, then you just need to calculate the initial rest mass energy, the final rest mass energy, and subtract these two. Then you will know if the reaction is feasible or not. So Thanks for watching, and I hope this video on radioactive decay.